Chapter 9, The Development and Aging of Body Systems. So this is a continuation of what we talked about in Chapter 8, which was more of an introduction to changes in physical growth and physiological maturation. Now we're going to talk about body systems individually. So I think a great way to start off is by going through what each body system is responsible for in the whole body in its entirety. So most of these should sound familiar to you because of anatomy. But the skeletal system defines an individual's structure, right? So these are our bones that create kind of a general outline of our body, right? And we get filler and shape from our muscular and adipose systems. So our muscular system is where our muscles are, right? So skeletal muscle, smooth muscle, cardiac muscle, and the primary function of our muscular system is to generate force and movement. Most often we kind of think about this in terms of moving around, and I guess if we're looking at this class, we could look at motor behaviors or motor skills. But remember that our heart also generates force and movement in terms of pumping blood throughout our body. And smooth muscle, which usually is located in our organs, is going to be responsible for generating force and movement of food, right? And other byproducts of digestion through our GI tract. So force and movement is the most general function of the muscular system. Our adipose system is where our adipose tissue is, our fat tissue. So this system plays roles in storing energy, producing energy, or providing substrates that can be metabolized for energy. There's storage of different chemicals and minerals and vitamins in fat. So if you think of an example of your DAKE vitamins, D, A, K, and E are all stored in fat tissue, or they're fat-soluble vitamins. Insulation for thermal purposes, and we also have protection. So if you think about different types of joint structures that are primarily built out of fat tissue, such as fat pads on your feet, right? They add an extra layer of cushion for your bones so that your bones are not directly taking on stresses of the world if for some reason you fall or are undergoing pressures or whatever, okay? In addition, we also have our endocrine system, which is going to primarily regulate hormones in our body, and those hormones are going to be instrumental in carrying out certain cellular functions. We'll also talk about this in terms of growth and development as well. And then lastly, we have our nervous system, which in my personal opinion, and I'm a little bit biased because I'm studying motor control, but the nervous system is probably one of the most expansive and impressive body systems in the whole body. So nervous system, if you think about it, is the connection between everything, right? Between our brain, which creates voluntary and involuntary signals, and it pairs all of those signals with our muscles and our organs and other various tissues. So the nervous system is super vast. I feel like we've come a long way in recent years, and we know a lot more about the nervous system, but there is still so much that is not known about the nervous system. So I think it's, in my personal opinion, it's the most fascinating one out of all of these. Although pairing nervous and muscular systems together is kind of along my line of interest, and so those are probably my two favorite systems to investigate. But my opinion does not matter. You can bias yourself to your favorite body system because they are all important and they're all integrated into whole body function, as well as development. So that's one key thing that we're going to start to kind of find out as we go through the lecture, is that all of these body systems are dependent on one another, and that dependence is critical for proper development, as well as some of the different types of aging that we see in body systems throughout the lifespan. So we're going to go through the development of each system based on the period of life. So what better place to start than the beginning? So we're going to start with prenatal development, or the prenatal period, when we still have an embryo or a fetus, right? So anything prior to birth. In the prenatal period, we kind of touched on this a little bit last week, as well as in previous lectures, in just talking about the different stages of development. But the stuff that happens during this period is super, super critical. And there's different periods that might be more critical than others. But in the embryonic stage, the skeletal system is a cartilage model. So there are no hardened bones yet. We're basically just like a little floppy piece of cartilage that makes up our little tadpole structure until we kind of get to the fetal stage, which we're just a cartilage model of a tiny human. But there are no ossified bones in the embryonic stage. As we get into the fetal stage, we start to begin the process of ossification, and this is going to happen at primary ossification centers, which exist primarily in the mid portions of long bones. If we're looking at other types of bones, such as irregular bones, short bones, sesamoid bones, etc., right, those are still going to have an ossification center, but long bones have ossification centers, or the growth that happens in long bones is slightly different than we have in other types of bones. So just know that bones ossify outward regardless of the type of bone that we're looking at. Long bones will specifically go into how growth continues after birth, which will be in our next section, outside of the prenatal period. So bones ossify outwards, or ossify, we could also say harden, or we're creating bone material. We don't really go deep into the different types of bone cells, but there is a process of cartilage being converted into bone that is happening during this period. And then typically we're going to notice bone cells around the 2-month period of the prenatal stage. So if you're thinking about this in weeks, it would be around the 8-week mark, when you have a relatively human-like structure. So again, kind of the beginning of the fetal period is when you start to actually see bone within the fetal structure. For the muscular system, remember last week we introduced two terms, hyperplasia, which is increasing the total number of cells, and hypertrophy, which is increasing the size of a given cell. So both of these are occurring in the prenatal period. Hyperplasia, however, is more dominant during the prenatal period versus hypertrophy, which is more dominant after birth. And this should make sense because your muscular system has its stem cells that are going to be proliferating into different fiber types, right? So we're increasing the total number of muscle cells to build individual muscular structures. And then after birth, when we start to engage with our environment and we're, conducting ourselves in more and more and differentiated activities, we can then start to build the size of those fibers and increase our muscular strength. So at birth, typically we see that muscle mass makes up about 25% of the birth weight. 15% of muscle mass is comprised of undifferentiated muscle fibers. So You'll remember that there are two primary types of muscle fibers if you've taken anatomy or exercise physiology. Type 1 are our slow twitch muscles that are primarily going to be helping us with endurance type activities. So they are slow oxidative. They produce, their metabolic processes are going to end up producing the greatest amount of energy because fat yields the most energy. They are kind of slow and low in the force production area. The other type of muscle fiber that we have are type 2 fibers, which are known as fast twitch, or kind of our muscle fibers that are associated with power type movements. And those can further differentiate into types A and X in humans. You can also add a type B in animal species. The two types, one is a fast twitch glycolytic, the other one's a fast twitch oxidative. So each is going to be helpful in producing power and big bursts of high force, but they use different metabolites for energy. So 15% of our muscle mass usually is considered undifferentiated, right? Either we don't know if it's a type 1 or a type 2 fiber. And then any type 2 fibers that have differentiated, 15% of those are undifferentiated between type A and type X. Okay? So there are current speculations in research that undifferentiated cells become either type 1 or type 2 based on the activities that babies engage in during early infancy. So if they're engaging in like pressing their chest up and holding that position for a long time, maybe they're going to have cellular differentiation into type 1 fibers. If they, maybe have a certain type of walker or baby seat that allows them to kind of squat and press, they do like the little bouncing thing that's kind of cute. But if they're pressing really, really hard into the ground or performing a lot of kicking actions, maybe they have differentiation into type 2 fibers. So it's speculation, purely speculation. It's not necessarily 100% backed by research, but it is an interesting thing to think about in terms of development. There also are genetic links to the type of fiber that you're predominantly, or the type of muscle fiber that you're predominantly going to kind of lean towards. So for myself, both my mom and my dad were power athletes. So naturally, my sister and I are both more along the lines of power athletes. Endurance has never been a strong suit of mine. And that's another thing to note, that sometimes you're just structurally limited, right? Some of us may not be good runners, we just can't run for long periods of time, but we're really great at sprinting, okay? That's in large part due to the muscle structure that develops from prenatal through kind of the end stages of after your fibers have differentiated. So, I don't know, I think those are kind of like really cool things to consider. Also in the prenatal period, we have our adipose system. Adipose tissue starts to appear in the fetal stage at about 3.5 months, and then will increase really rapidly in the last 2 months of the prenatal period. And it accounts for about 1 pound of the total body weight at birth. So typically babies are anywhere from, average weight is anywhere from 6.5 to 8-ish pounds. So adipose tissue makes up a good chunk, and if you think about it, babies are very chubby when they're born, which kind of adds to their appeal, but it's functional. If you think about it, because they're very unstable, and we mentioned that adipose tissue has a function for protection, so they have extra cushion if they need it. Lastly, our endocrine system. There are a large number of hormones that are vital for optimal prenatal development, and the regulation of the hormones through that placental bonding between mother and baby is really important, because like we said last week, anything that the mother takes in is going to be directly passed to the baby if that placental membrane allows for passage of certain materials or chemicals or other types of substrates. So hormone regulation is super, super important. The book really doesn't go into a lot of detail of prenatal endocrine system just because it's really, really complex. But just know for this stage that hormones that pass from mother to baby are really important for prenatal development. I think that's kind of the key point we want from this slide. Lastly, the nervous system probably undergoes the most development in the prenatal period, and I've got some fun facts that are quite fascinating. But the nervous system undergoes 3 primary periods in the prenatal stages. The first one is neuron formation, the second is differentiation, and the third is migration. So neuron formation is just the building of neurons or nervous cells. So nervous cells or neurons are comprised of a cell body, which in the picture to the right can be seen where my cursor is. So it's this big yellow thing with all of these little branches sticking out of it. Those branches are called dendrites. Those are the receiving ends of the neuron. So if you have an adjacent neuron that has its kind of synaptic or axon terminal ends over here, those send signals or transmit signals from this neuron to another neuron, which would receive information through its dendrites. And then the axon is kind of our area of impulse transmission. So this is where our signals get passed through. And there are different structures that are included on this axon. You see these little blue casings that kind of look like the dividers that you see in like swimming pool races. I don't know why that sounds so awkward. But myelin is present on a majority of our neurons in our nervous system. You can have some unmyelinated neurons, but myelin is going to be really important for the speed of neural transmission or impulse transmission. And basically what happens is, it's kind of hard to read, but in this figure, the little space between our little myelin sheaths is called the node of Ranvier. It's named after the guy who discovered them. But basically, once we get a receiving signal, if it sums up to something that this neuron, determines that is a critical piece of information that needs to be sent to another neuron, that generates an action potential that's going to travel down this axon. And when we have a myelinated axon, from sheath to sheath, we have node to node, right? And that signal is going to jump from node to node. So you can see that signal transmission would be a lot faster than if we just had a regular axon in which the signal would have to travel down the entire length of the axon. So instead, we're kind of skipping to the ends, which is our axon terminal or our synaptic buds. There's a lot of different names that I've come across in anatomy for neural, or at least like the synapse anatomy. But synapses, these are technically spaces between the sending and the receiving ends of neurons, and what's sent across these spaces are different types of neurotransmitters, and we're not going to get into the neurotransmitter aspect, but a bunch of different types of neurotransmitters have different excitatory and or inhibitory actions. So that kind of ends up determining the behavior that results from this neural signal. Okay, so prenatal period starts with neuron formation, where we're just building these structures. The second phase is differentiation. So we start with some type of embryonic stem cell that becomes a neural stem cell, and then we have this proliferation period where we're just building a whole bunch of neural stem cells, and they just keep dividing and dividing and dividing and multiplying, actually at a rate of 250,000 neurons per minute. That's crazy. If you think about how many minutes are in 40 weeks, which is the average gestational period, like multiply that number by how many minutes, and that's how many neurons you end up getting, which is nuts. It's absolutely crazy, right? We have all of these neural stem cells that are proliferating and multiplying, and then all of those proliferated cells are going to differentiate into different types of nervous cells. So the neuron is the most basic cell, and that's the one that comprises the majority of our body. But we also have other types of cells, like this one in this picture is called an astrocyte. And we don't really talk about different types of neuron cells or nervous cells, but there are different types, just so you know. But between the 3rd and 4th prenatal months, typically brain neurons are fully developed. Remember, we said that typically growth is going to happen in a cephalocaudal direction, starting from the head, moving towards the tail. And this is why, right? Because we have to formulate the brain first so that the rest of our organs and other body systems can start to develop in the way that they're supposed to, and we're building the connections that we need. But by the 3rd or 4th prenatal months, typically there are about 200 billion neurons total in the body, which, again, it's a crazy number. And that, I believe that 200 billion is just in the brain, because we're still proliferating out into the body, which is the last stage that we call migration, right? And so usually migration starts around the 6th prenatal month, and this is where we get migration throughout the body, right? So neurons are going to be, we have like the brain and the spinal cord that make up our central nervous system, and then we have this migration of the peripheral nervous system to different organs in our thorax, to different plexi that extend out to our extremities. And so we get specialization based on primary location and function. Okay, so example, the brain stem is going to have neurons that specialize to regulate heartbeat, breathing. We've got neurons that are going to branch out of our, thoracic plexi, that will be responsible for the, workings of our stomach or our spleen. I don't know. Kidneys, right? Any organs that are in your abdomen, which there are a lot. And then we also have our nerves that kind of extend to our muscle tissue that create motor units, so that we have that neuromuscular control and connection. There's also nerves that go through the dermal layer of the skin, right, that are going to specialize for thermal regulation, or not thermal regulation, but thermoreception, mechanoreception, or mechanosensation. Nociceptors or nociceptors are going to kind of help us with perceiving pain, right? So lots of different specializations that can happen with all of these nerves that are extending and migrating throughout the body to their final destination. Neurons will elongate to create synapses with other neurons, which kind of at the 6th prenatal month, we have about 100 trillion neurons in the body, which, I mean, previous slide, you thought 200 billion in the brain was a lot, right? 100 trillion in the body is just really crazy. But this part of our prenatal period, this migration part, is also really important, because if we have faulty migration, that could lead to different neurological disorders, which could potentially be bad later in development. But neurons are generally going to be in competition with each other. So as they migrate, they kind of compete to see like who's going to create the most efficient neural circuit. Neurons that don't create a strong enough connection with that given circuit die out. So I like to think about this as like the bachelor version of the nervous system, where you have one really strong nerve or neuron from the central nervous system that's starting to branch out and make connections, and there maybe are like 20 different neurons. I don't know, I'm coming up with this stuff now. But there's like 20 different neurons that could make a single connection with that one neuron for a certain neural pathway, but only one wins and the rest of them die out. Which is why we kind of have this concept of redundancy in the nervous system as we're building it, and why we have so many neurons is so that we create the best connections possible for the rest of our life. Right? But like I said, if we kind of have that faulty migration, we get different types of neural disorders. Some examples that the book gives are epilepsy, autism, dyslexia. But also, the nervous system is really susceptible to teratogenic exposure. So we talked about teratogens, or different types of toxins, or kind of poisonous substances that could negatively affect development in the prenatal stages. And the nervous system or teratogenic exposure usually is the most critical in, I think last week I said like the 6th week of development, because that's when the placental or the placenta is kind of fully developed, and when we start to really transfer blood from and different types of blood contents from mother to baby and vice versa. So improper neuron migration as well as teratogenic exposure usually going to lead to low IQ, right, or kind of improper development of the central nervous system before it starts to expand out to the rest of the body, or mental retardation. So usually teratogenic exposure is going to negatively affect the central nervous system more than the peripheral nervous system. But firing, lastly, is kind of random in the prenatal stage, and then it starts to become more organized during the postnatal stage after birth, right? So a lot of times people are like, oh, my baby is kicking. These are more or less spontaneous movements that we see after birth, or reflexes. We've talked about some types of prenatal reflexes that happen prior to birth. So that movement or that random firing pattern is kind of a solidification of different reflex patterns, as well as just spontaneous movements that we know have a connection to voluntary movements later in life. But random firing is something that happens in the prenatal period. That kind of concludes the prenatal period as a whole and the different body systems and their development, which brings us to our next big stage of development, which is childhood and adolescence.